Hi, this is Dr. Emenacker. Welcome to this video in the differential equations sequence. We're going to look at integrals as solutions in this particular video. Hi, this is Dr. Emenacker. In this particular video, we are going to start looking at ways to solve ordinary differential equations. There are two types of differential equations. There are equations like what you see written down there, which are called ordinary differential equations. There are also what are called partial differential equations. Partial differential equations involve partial derivatives. So it's real easy to pick them out, and they talk about it in the book and things like that. I haven't spent a great deal of time on it. Um, but realize that if it has partial derivatives, it's a partial differential equation, abbreviated as a PDE, and that's a whole group of differential equations in and of itself. And this semester, we're going to basically focus on ODEs, which are ordinary differential equations. They have no partial derivatives in them. Okay, so if we take a look at what we have going on right here, where we have dy dx equals f of xy, what we basically have is on the left-hand side, the derivative of y with respect to x equal to some function. This function can have the variables x and y in it, and we'll see that as the semester goes on. You can either use the Leibniz notation for the derivative, which is the dy dx, or you can use the Newtonian abbreviation y prime. Either way, it's the derivative of y is equal to some function. The unfortunate thing about differential equations is that there's not one way, an easy way, that always works to solve anything in the form of y prime equals some function in terms of x and y. Let's start with a relatively easy problem, and as the semester progresses, we'll take a look at more entertaining problems. If we have something like y prime equals a function, now on the right-hand side, this function could be anything in terms of x and y. It could just be something as simple as x. It could be something like x plus y. It could be much more involved with higher um, exponents and natural logs and trig functions and exponential functions and all kinds of crazy stuff going on. Okay. But what I want to remind you here is that we're going to basically see things that are in the form where the derivative is equal to some function. Now, going back to Leibniz notation, that equation can be written as dy dx is equal to the function, or you can actually multiply both sides by dx and have the dy, the derivative of y on one side, and then the dx on the other side with the function that we're working with. In order to solve an equation like what we have here, we want to compute the antiderivative of both sides. So what I'm looking at is I have taken my function, I have rewritten it like this, where on the left side I have the derivative of y. And on the right-hand side, I have my function and the dx. So I have it there. And what I'm doing is I'm going to apply the antiderivative to both sides. On the left-hand side, when you apply the antiderivative to the derivative, they are inverse functions, and they cancel out, and you get y in terms of x. On the right-hand side, we still have our antiderivative plus a constant. You may or you may not be able to actually perform the antidifferentiation or compute the definite integral. Not sure if you're going to be able to or not. There are a lot of cases, and there are some that we're going to see even today, where you just can't do that. Pulling back to some of your earlier experiences in calculus, recall the fundamental theorem of calculus says that if we have a function where we have the integral of f of x dx, that can be written as the integral f of x dx from x0 up to some other value of x. And of course, you still have the plus c. So just reminding you that the fundamental theorem of calculus allows us to rewrite it like this. That's going to come in handy as this video progresses. Let's take a look at a specific case. Let's say we have y prime equals 3x squared. We can rewrite this as dy equals 3x squared dx, okay, and then compute the antiderivative of that. The antiderivative would look like what we have here, and of course you're able to work that out. In solving this problem, what you're going to wind up doing is applying the antiderivative to y prime, which will give you y, and it's going to be in terms of x. And then, of course, when you integrate 3x squared, you get x cubed plus c. So that gives us our solution that we have down here. Now, oftentimes there's going to be an initial condition. This initial condition is going to be some starting position, height. It could be a temperature, all kinds of things. It depends on the problem that you're working on, but oftentimes there is information about the system at the start. This initial condition is often going to be y at x0 equals y0. x0 oftentimes will be a time, and the time might be 0. So we're often going to see that the x0 value is just going to be 0. Okay, it will not be at all uncommon for x0 to equal 0. So for example, at the start, times 0, aha, there's x0 equals 0. That doesn't mean it has to always be that way. Let's take a look at something like this. Suppose we have a general situation where we have y prime equals f of x, and we're given some initial condition. Y at x sub 0 is equal to y sub 0. Well, if we go ahead and we solve this and apply the antiderivative to the y prime, we're going to get y. Apply the antiderivative to f of x, and we're going to get this integral f of x dx, and normally we would get plus c. Okay. Now this can also be written as, if you'll recall, y of x equals x sub 0 to x of f of x dx plus y sub 0. And the question is, when you do something like this, does the initial condition really satisfy the solution, the proposed solution that we have? Well, what we can do is we can say that the y value evaluated at x0, whatever that might be, is going to be equal to our integral plus, and recall y0, aha, there it is, okay? So what's going to wind up happening here is we're going to take our value for x sub 0, substitute it in there. Then in our notation where we integrate from x0 to x, our x value in this case is actually going to be x0. And if you'll recall, when you integrate from x0 to x0, which is what we're doing right here, when you integrate over that distance, which is a distance of 0, you wind up with the integral equal to 0. Just a quick reminder, integrals talk about areas. If you have an area that has some amount of height, but no width at all to it, of course, the area is going to be the width times the height. And if the width is 0, x0 to x0, the area is 0. So that gives us then that this whole integral is going to be 0, which leaves us then with y of x0 equals y0. But hey, we already knew that. That's our initial condition up here. That's this. So it truly does work as a solution. Okay, so with that in mind, let's take a look at something like this. Let's say we have y prime is equal to e to the negative x squared, and we're given an initial condition of y of 0 equals 1. This means that when the x value is 0, the y value is 1. You may recognize this e to the minus x squared. It's actually something that's used in statistics. And in fact, it's used to create the bell curve. That function e to the negative x squared is what produces the bell curve, which gives us the probability of, or allows us to then compute the probability over a normal distribution. All right. So using the idea from above, I'm going to take this function, I'm going to apply the antiderivative to both sides, which is going to give me the integral of y prime equals the integral from x0 to x of e to the negative x squared dx. And notice here I have a plus 1. This plus 1 comes from the value y sub 0 equals 1, which is that information right there. Okay, so with that being the case, we wind up with being able to rewrite this. We know our x0 right here has the value 0, which allows us to then rewrite our lower limit as 0 up to x e to the negative x squared dx plus 1. Now, there are going to be situations that we encounter this semester where you cannot integrate or compute the antiderivative. This is one of those cases. In a situation like this, you just leave it alone. Well, you can use numeric techniques to evaluate this on a computer and estimate the value going from 0 up to some amount. And that would then give you the probability between 0 and whatever the amount is, with 0 being at the um, center of the normal distribution. So your 0 would be right here. Okay. And you can work from there as far as however many standard deviations you need to move. Okay. So it's important to remember that not every problem has a solution. Some solutions wind up just involving the integral like that, and you then need to use numeric techniques, computers, good stuff like that to figure out what's going on to estimate it. Let's consider something like this. This is a problem that we looked at earlier. This is the problem where we say, okay, if I take the derivative of the function, I get the function back. That's what this says. Okay, if I compute the derivative, here it is, and I work that out, I get back what I started with before I took the derivative. Now you may recall from an earlier section, we found that the solution to this was c to the kt or c to the kx or c to the rt or some form like that where you have a constant times e to another constant times whatever the variable is. Oftentimes, if you're working in particular with things like interest rates, the amount that you have at any time is equal to the amount you start with, e to the r, the interest rate, times the amount of time. Okay, so there's another form of this exact same solution where we have c e to the kt. All right, how do we solve this? Well, we're going to pull back to some of our information that you should have learned in Calc 2. The inverse function theorem is what we're going to reference at this point. And using the inverse function theorem, we're essentially going to reverse the roles of x and y in the problem. If we reverse the roles of x and y in the problem, it allows us to rewrite this left-hand side as dx over dy. And what the inverse function theorem says is that if you reverse the roles of x and y, what you wind up with is the inverse of the function. So what we're going to have here is not dy dx equals f of x, but what we're going to have is dx over dy equals 1 over f of y. Okay, so what's that get us? Well, what that allows us to then do, let's move this up a little bit here, is I'm going to multiply both sides by dy. So on the left-hand side, I'm just going to have my dx. And on the right-hand side, I'm going to have my 1 over f of y is going to be equal to, make sure that doesn't ring again, is going to be equal to 1 over f of y dy. Apply the antiderivative to each side. On the left side, I'm going to get x. And my x is going to be written in terms of the variable y over on the right side. On the right-hand side, if we have 1 over the function, when we apply the antiderivative, we get the natural log of whatever the function is plus some constant of integration. Okay, if you'll recall, when we solved this earlier, we said that the solution was y equals e to the kx, assuming k is greater than 0. What I would like you to see is that we can actually derive or obtain that solution from this equation that we have going up here. Okay, so what we're going to wind up doing is we're going to use the inverse function theorem, and we're going to assume that y is not 0. Okay, and we'll take a look at several problems down the road where we deal with the possibility of y equals 0 being a solution or not being a solution. But for right now, what we're going to do is we're going to start out with our initial problem where our derivative is equal to some constant times y, the original function. I'm going to apply the inverse function theorem, reversing the rules of x and y here. So I now have dx over dy. And what that says is on the right-hand side, I'm going to have 1 over ky. I can then multiply both sides by the dy and apply the antiderivative to each side. When I apply the antiderivative to the left side, it gives me x in terms of y, which notationally is shortened to just be x. On the right-hand side, notice what I've done. This 1 over k is a constant. It's just some number. You can bring that out in front of your antiderivative. So we have 1 over k times the integral 1 over y dy. Well, when we do the antiderivative of 1 over y dy, it's going to give us this natural log of y, and then of course we need to include a constant. All right, at this point now, we have things in terms of x equals. But what we want to do is we want to reverse this so that we wind up with something in terms of y equals. That means that we need to now take this equation right here, and we're going to solve for y. Well, the first thing I'm going to do is I'm going to subtract d from both sides, which is going to give me my x minus d. Then, in the same step, I'm also going to multiply by k. So I'm going to first subtract d, multiply by k, which gives me k times x minus d, all on the left side, equals to the natural log of y on the right side. Well, what I really need to do now is first I'll distribute the k, so I have the kx minus kd. I have d times k, it doesn't really matter. Okay, they commute, equals natural log. I'm going to apply e to both sides, e being the inverse of natural log, which when you apply it to this right-hand side, the e and the natural log will cancel, giving us y equals. When I apply e to the left-hand side, I wind up with e and all that other stuff in the exponent. This can be broken up into two separate factors. I'm going to have e to the k times x times e to the negative k times d. Now remember, k is a constant, d is a number. When you take e and you raise it to some number, you just get a number. So we can look at this whole thing here as just being c. Don't know what the number is, but we can find it if we need to, and we're given an initial condition. Rewriting that whole thing as c allows us to then take this function here and rewrite it as y equals to c e to the kt, which is the solution that we came up with and discussed earlier. Okay, if you'll recall, somewhere up here, here we go. We had said, you know, the solution to this particular differential equation is going to be c e to the kx. Didn't really derive it at that point, but now you've seen the derivation of that solution. Let's take a look at something like this. Let's say you're asked to compute the general solution for y prime equals y squared. The first thing you always want to do is to ask yourself, does y equals 0 work out to be a solution? In this case, the answer is yes. Now you may be looking at that and saying, I don't see how this is an answer at all. Well, on the left-hand side, it says take the derivative of y. Well, the derivative of 0 is going to be 0 equals, on the right-hand side, we're going to take 0, which is our y value, and square it. And 0 is equal to 0 squared. So before we even start, we have a solution to this equation. Not a very interesting one, but at least we have a solution. So what we're now going to do is we're going to rule that out, and we're going to assume that we're going to look for a solution that does not involve y equals 0. So we're going to have y not equal to 0 for the rest of this. First thing I'm going to do is I'm going to take my y prime and rewrite it using Leibniz notation as dy dx equals y squared. I'm going to apply the inverse function theorem, reversing the roles of x and y, and I'm going to have dx over dy equals, and remember with the inverse function theorem, the function on the right-hand side now becomes the inverse of what it originally was. So we're going to have dx over dy equals 1 over y squared. From there, I can go ahead, multiply both sides by dy. Okay. And that's going to give us the equation dx is equal to 1 over y squared dy. I can apply the antiderivative to each side. Remember, 1 over y squared can be written as y to the negative 2 and integrate. Okay, so on the left side, what we wind up with is x in terms of y, which we're just going to shorthand to be x equals. On the right-hand side, we've got the antiderivative of y to the negative 2 is negative y to the negative 1. Now you may be sitting there thinking, I'm not sure about that. Okay, you add 1 to the exponent, negative 2 plus 1 is a negative 1, and then you divide by that new exponent, so we're going to negative y to the negative 1 as our result. And then, of course, we need to include our constant of integration. This can be rewritten as negative 1 over y plus c, which then gives us x is equal to this negative 1 over y plus c. Okay, when we apply the inverse function theorem, we reverse the roles of x and y. What we really need to do is to ultimately compute what is the value of y. So we're going to take this solution that we have here, and we're going to solve for y. So the first thing I'm going to do is subtract c. Then I will multiply by a negative 1, which is just going to reverse the positions of the c and the x because it's a difference, it's subtracting. I have 1 over y equals that, which gives me y is equal to 1 over c minus x as a solution. And remember, we still have this solution that we determined right at the start of the problem. So there are two solutions to this problem. Let's take a look at this solution that we just obtained, this y is equal to 1 over c minus x. This has a singularity where x is equal to c. If we were to take the value c, plug it in there, you're going to get 1 over c minus c, 1 over 0, undefined. The graph of this function is going to look like what we have here. It'll be continuous to the left of our singularity being c, whatever that number is, and we'll wind up with something like the left side of this graph. To the right of c, we're going to get something that looks like this side of the graph. Okay. It's kind of interesting to notice that our original function, y prime equals y squared, is defined on the domain from negative infinity to infinity, but our solution has a different domain. It goes from negative infinity to c, union with c to infinity. This allows us to omit the singularity. Okay, so you can wind up with a different domain on your solution than you had on the original equation. That's important to keep in mind. If we have an initial condition, for example, y sub 0 equals 2, I just made up something. The solution, y is equal to 1 over c minus x, is going to give us, well, let's see, the y value is 2 when the x value is 0. When I substitute those values in for y and x, I can then solve for c, and I get a c value of 1/2. In this case, the domain, using the information now at the top of the screen, is going to go from negative infinity to our value of c, 1/2, union with our c value, 1/2, to infinity. So we have a singularity in the solution at x equals 1/2 when we apply the initial condition y at 0 equals 2. That singularity will move around as we wind up with different values, okay, for the y. In some cases, even the x value itself might change. The x value might be 1, it might be 10, who knows? All right, let's take a look at something a little more physics oriented, something a little perhaps more concrete to you. Suppose we have a situation with a car or something that's accelerating, and the velocity is equal to e raised to the t over 2 meters per second, with t in terms of seconds. Nothing fancy. The question is, how far does the car travel in 2 seconds when, aha, we're given an initial condition? Here, our initial condition says when the time is 0, the position, x, is 0. So at time 0, it's at the start. And in this problem, it doesn't say something that would lead us to believe that we have something other than a start time of 0. If you were given something like an initial condition of x of 3 equals 14, that would say that what we're going to look at starts at the 3-second mark, and at the 3-second mark, we are 14 feet, meters, whatever it is, away from the initial position. Okay, so these initial conditions can change the problem a good deal. Okay, let's think back to some of your calculus and some of your physics. Recall that velocity is the derivative of the position equation. Okay, so I can take this equation that we have up here, where I have v equals e to the t over 2, and I can write this as v of t, or I can write it as x prime of t, okay, because the velocity is the derivative of the position equation, equals to e raised to the t over 2. With this, I now have the opportunity on each side to anti-differentiate. And in this case, remember, if we wanted to write this in Leibniz notation, this would be dx over dt. The variable's name is dt. Okay, so when I apply my antiderivative to each side, after I've multiplied both sides by the dt, because remember this is dx over dt, I can multiply both sides by my dt, which is how the dt ends up over here. Okay, applying the antiderivative, the integral e raised to the t over 2 dt becomes 2 e to the t over 2 plus c. Now, it may have been a while since you've done your integration, and you may be sitting there thinking, I'm not quite sure how that worked or where you got that. Just a quick reminder, one way to solve this is we can let u equal to t over 2, du is 1/2 dt, or we get the dt is going to be 2 times du. The dt here can be replaced with 2 times du, and then we're going to have e no longer to the t over 2, but t is going to be, or I'm sorry, the t over 2 is now going to be replaced with u. So we have as the integral e to the u 2 du. The 2 can come out front, and what we're actually going to do then is we're going to be integrating e to the u, which is just e to the u. We have our coefficient out front, our 2. We get our e back, replace u with t over 2, and there you have it, just in case you forgot about how do we do something like that. Okay, so we now have our position equation, x of t is equal to 2e to the t over 2 plus c. I'm going to substitute in my initial conditions. Remember that when x is 0, or in this case t is 0, I should get back a value of 0, which gives me then the equation 0 is equal to 2 e to the 0 power plus c. Now be real careful. People are kind of quick to say, aha, it's 2 times 0 plus c and c is 0. No, e to the 0 power is 1. So what this is actually going to simplify to be is 2 times 1 plus c. 2 times 1 just being 2. Subtract 2 from both sides and you get c is equal to a negative 2. This then allows us to rewrite our equation. Our solution is 2 times e to the t over 2 plus our c value, but our c value is a minus 2, and there you have it. This satisfies the condition x at 0 equals 0. To verify this, what we need to do is to recall that our t value is going to be 0. So I'm going to substitute a 0 in here, and the value that comes out should be 0. So what I have now with 0 substituted in for t is 2 times e to the 0 over 2 minus 2. This really works out to be 2 minus 2, which just like back in first grade equals 0. So what this does is it allows us to check, and yes, our initial condition does satisfy the equation, and the equation works with that initial condition. The question that we're asked here is, what is the distance traveled in 2 seconds and at 10 seconds? Well, the nice thing here is that we can go ahead and substitute t equals 2 into each equation. So if I take my t value of 2 and substitute it in here, I have 2 times e minus 2 equals about 3.44 meters. And then if we were curious how far has this thing traveled in 10 seconds, I'm just going to take my value of 10, substitute it in for t. We get 2 times e to the 5th minus 2, which works out to be around 294 meters. Let's look at a different start and initial conditions. Suppose we have x double prime equals t squared. Notice our function on the right-hand side is no longer e to the t over 2, but it's just t squared. And very importantly, notice on the left side we have x double prime. Remember, if x of t is the position, that means that x prime of t is the velocity, and then x double prime of t is going to be acceleration. Okay, so that's where that acceleration written in orange comes from, is that information. Okay, first thing I want to do is I want to compute what is the velocity. Well, the velocity is the first derivative. That means I need to go from the second derivative to the first derivative. To do that, I'm going to go ahead and I'm going to integrate or apply the antiderivative to both sides. When I apply the antiderivative to x double prime, it becomes x prime. When I apply the antiderivative to the t squared, I get 1/3 t cubed plus c. At this point, I can use some of my initial condition information. Now you've got to be really careful, because up here in my initial conditions, I'm given two pieces of information. I'm given x of 0 equals 1 and x prime of 0 equals 10. Right now, I have x prime, so I need to use the initial condition that talks about x prime. and my initial condition is x prime of 0 equals 10. Okay, so that initial condition information tells me that my left-hand side is going to be 10. And on the right-hand side, wherever there's a t, I'm going to substitute in 0. So it's going to give me 10 is equal to c, which then allows me to rewrite my first derivative, my position, or I'm sorry, my velocity as 1/3 t cubed plus c, which in this case is 10. Now, I now have a position equation, and from that, I want to determine distance or position. So what I'm going to do is I'm going to once again apply the antiderivative. Okay, and I'm going to apply the antiderivative to both sides. And what this will give me then on the left side is I'm going to have my x of t, which simplifies to just be x, equals. When we apply the antiderivative to this, we're going to increase the power by 1 and then multiply by 1/4, which is going to give a 1/12 t to the fourth plus 10t plus c. As before, I need to be careful to pick up the correct initial condition. The initial condition in this case is that x at 0 equals 1. This means something in the physical realm. This means that at time 0, this object is 1 foot, 1 meter, whatever the unit is, it's 1 unit away from the starting position at the start. Okay, so maybe it gets a head start or something like that. So what this allows us to do then is to substitute 0 in for t, and the value that we should get back is 1. Okay, so the 1 is going to be over here, and then I'm going to substitute the 0 in each location where there is a t. When I do that, that allows me to solve for c very readily because this is just 0, this is 0, which gives me that c is 1. I can then rewrite my position equation as x of t is going to be 1/12 t to the fourth plus 10t plus my c value of 1, and there it is. We can now compute for the value of the position at time 10 seconds. That's what this means. This says figure out how far this is away from the start in 10 seconds. All we need to do for this is to substitute 10 in for t in each location and plug it into the old calculator, and we find that the position in 10 seconds is 934.33 meters. Okay, that should give you some stuff to think about. Be sure that you take a look at the homework for section 1.1.